Okay, Matt Roscoe here with our course Math 133, Geometry for Elementary School Teachers, and a lecture on polyhedra and other solid shapes. So this is the start of chapter 13, which only has 4 sections. It's going to be a fairly quick chapter to run through. If you look at the syllabus, you'll see that this is only going to last a couple weeks. We'll take a couple days on chapter 13.3 since it's the long one. But the majority of the chapter has to do with finding surface area and volume of solids. So before we dive into finding the surface area and volume of solids, it's helpful to sort of go through and take a look at how are solids defined. So that's what this first chapter is about, is how can we categorize and define the different types of solids that we're going to want to find the surface area and volume of. So we're going to take a look at the definition of polyhedra, then of prisms, pyramids, cylinders, and cones, and then we're going to take a look at a special set of polyhedra that are called the regular polyhedra, sometimes, well, more commonly called the platonic solids. And then we're going to take a look at a really interesting relationship that has to do with vertices, edges, and faces of any prism, actually any polyhedra. So let's start out right away by talking about what a polyhedra is. A polyhedron is a closed, connected shape in space whose outer surfaces consist of polygons, such as triangles, quadrilaterals, pentagons, and so on. So you can see here a whole big set of examples where everything here is a polyhedron. So you can see it's a really broad definition. Polyhedron just means that this is some sort of shape that exists in 3 dimensions whose faces or outer surfaces are polygons, so they can be named according to the edges. So, you know, for example, if I look at this red guy down here on the lower left, I can see that it has faces that are triangles and rectangles, and it's a closed connected shape in space. And of course, triangles and rectangles are examples of polygons, so this guy satisfies the definition of polyhedron. If I go over here to this blue one on the other side, I can see that this guy has 1, 2, 3, 4, 5, so it looks like pentagons for top and bottom, and then rectangles for sides, so certainly a polyhedron. Oftentimes there's mixes of shapes that are, a mix of here pentagons and rectangles, mix here of triangles and rectangles, but sometimes the sides are all congruent polygons, as is the case back here with this purple one. You see all the shapes are, well, no, sorry, there's a square in there. I thought those were all congruent, but they're not. So I think everything here are mixes. Here we see hexagons and pentagons, and here we see squares and hexagons in this one here in the middle. But the idea, I guess, is that these are all examples of polyhedra, closed connected shapes in space whose outer surfaces consist of polygons, triangles, quadrilaterals, pentagons, etc. I will make a point to say that those, I guess, polygons that make up the outer surfaces don't have to be regular polygons. So we see, again in the example here with this red figure on the left, the triangle is certainly not a regular triangle. It's not equilateral, so it's possible for those shapes to be not regular, although lots of them here do have regularity, I see. So let's take some time here. Would you go ahead and stop the video at this point after asking yourself which of these solids are polyhedra? So A, B, C, D, E, and you can see this one's supposed to be labeled F. It's hard to see. G, H, I, J, K, and L. So make a little list, pause the video, and decide which one of these are polyhedra. Go ahead and pause the video now and do a little self-check. Okay, so hopefully you're back now after having sort of made a commitment. Let's go ahead and reveal the answers. So A is definitely a polyhedra, B is definitely a polyhedra, C is not a polyhedra. The reason that is that the faces here on C are not polygons. In fact, the one face is a circle and the other face is some sort of a curved, I guess, sort of like a label on a soup can. D would definitely be a polyhedra, E is a polyhedra, F is not a polyhedra, that's a sphere. Doesn't have faces that are polygons. G is a polyhedra, H is a polyhedra, I is a polyhedra, J is a polyhedra, K is not a polyhedra, it's a hemisphere, and L is not a polyhedra. This would be a cone. The reason K and L fail, of course, is because they don't have faces that are polygons. Okay, so hopefully you've got a sense of what a polyhedra is. Let's move on and talk a little bit about what prisms are now. So prisms are a special class of polyhedra, or subset of polyhedrons, in which two congruent polygonal faces, which we call the bases, lie in parallel planes, and whose remaining faces are formed by the union of all line segments that join the corresponding points in these two bases. So the idea is that if you have an equilateral triangle, and I repeat the equilateral triangle back here, and then connect all the vertices between these two, I guess, congruent polygonal faces, then what we get is we get a triangular prism. The next one would be a square prism. In other words, we have two squares that lie in parallel planes, and we connect all of the vertices. And then here would be a pentagonal prism. So we have two pentagons that lie in parallel planes, vertices connected. Hexagonal prism, octagonal prism. This is, I think, a 1, 2, 3, 4, 5. Yeah, I think this is a 10 decagonal prism. I don't know, decagon prism, a 10-sided prism. So the faces are decagons, and edges are all connected. So it is kind of neat. There is a really beautiful piece of software that you can use to explore this. It's called GeoGebra. My little link is not working on that, so I'll just go ahead and pull it in here and show you how to search it. So if I do geogebra.org, you get to here, and you can see that there are different math apps that are available, and the one I'm going to go to is this 3D calculator. This is at geogebra.org. So maybe just watch me do this first, and then you could play around with it yourself. While you're in there, there are different things that you can do in here, and unfortunately it assumes you want the calculator. What you really want are you want these tools over here, and I would encourage you to get more tools. And one of the tools down here towards the bottom are solids. You can build solids here in three-dimensional space. One of the tools that's kind of fun to build with is the prism tool, and it tells you that you're supposed to select a polygon for a bottom and then select a top point. Let's just play around with this a little bit. So I'll put a point at the origin, I'll drag it out to this point here, I'll drag it over here, and then back to the origin. So I have a polygonal base, so a polygon for a base. And then if I just sort of drag it up the y-axis, I get that. And of course what we see here now is an example of a prism. I'll go back to the move tool, and then you can kind of drag this and play around with it to see what it looks like from different angles. And what's kind of neat about this is that it gives you a dynamic view of what it means to be a prism. Of course I can change what these points that define the prism are, where these points are. So we see all kinds of different examples of triangular prisms here, but the important part that you realize is that when I look through it, of course, all the cross sections are equal when I look through the two congruent bases. So if I slice this like a loaf of bread, I could have triangular toast. That would all be equal in shape. So triangular prism, kind of a neat thing to see. I'm going to go ahead and select all, so I'll do Control A and delete. Let's take a look at a prism that's something other than a triangular prism. How about something with, I don't know, how about a pentagonal prism? So there's an example of a pentagonal prism. There are 5 different edges, I guess, to the congruent bases. So that means that the bases themselves are pentagons. And if I move it around, you can kind of see how this thing looks from different angles. It is definitely a fantastic piece of software, and of course it's free, which is really neat. So go ahead and try this out on your own if you have the chance and some time. Again, the idea is that any of these points are movable. Here we have still a pentagonal prism, although that pentagon looks really funny. We can move this down here and be pentagonal prism still. We can move this in here or out here, but these are all examples of pentagonal prisms. So I hope that gives you a good sense of just what I mean, I guess, when I say prism. So let's do a self-check again. Why don't you go ahead and pause, and after you hear the question, but will you tell me which of these solids are prisms? So now we're asking which ones are prisms. Let's take some time. Go ahead and pause the video for a second here and decide, make a list, and then I'll reveal the answer. All right, back again. Let's talk a little bit about which one of these would be considered prisms. Well, A would certainly be a prism. In fact, it's a hexagonal prism because it's a hexagon top and bottom, and they are congruent and in parallel planes. B would be either what we call B would be either a rectangular or a square prism, because it has either, you could classify it either as rectangle or a square as its bases. C is not a prism. Even though the bases are parallel in parallel planes, the bases are not polygons, they're circles, so that makes C not a prism. D is a pentagonal prism. E is a triangular prism. F is not a prism. G is not a prism. H is not a prism. Now I is a really interesting one. This one you could name one of two different ways. You could call this a rectangular prism if you viewed the two rectangles the way it sits. The one that's on the table, and the one that's above that has labeled I as the bases, then it would be a rectangular prism. Now if we turned it on edge and made this side over here the base, it looks to be a square, and so would the other side, so you could also call it a square prism. So either rectangular or square prism would work for I. And J is not a prism, K is not a prism, and L is not a prism either. So I hope that gives you a sense of what the prisms are. So we do have different types of prism. It turns out that you can have a right prism. It's a prism whose lateral faces other than the bases are all rectangles, so that's the case with the figure A. That's a right, I guess what we call it, a right, 1, 2, 3, 4, 5, 6, right hexagonal prism. Whereas an oblique prism is a prism whose lateral faces other than the bases are not all rectangles. So you can see here that what we get when we sort of squat or tilt, I guess, the prism is that we get parallelograms for at least a few of the faces here. And those ones are called oblique prisms. So the one on the right, it looks like we have a pentagonal oblique prism. I will say that these things seem to be less useful to us as humans, so we see very few oblique prisms in the world. We see lots and lots of right prisms in the world. So let's move on and talk about pyramids. This is a class of polyhedron, and it's a polyhedron determined by a polygon and a point, not in the plane of the polygon. So the polygon is called the base, and the point is called the apex. So here we would say that the polygon and the base is a square, and the point up here we would call the apex. So this would be an example of a square pyramid, and this would be an example of a triangular pyramid. So triangle is the base, and a point up here is the apex. Now just like in the case of prisms, we have right and oblique types. A right pyramid has a base that's a regular polygon, so here's a regular polygon, square, and faces that are congruent isosceles triangles. So that means all of these faces on this one on the left, A, are congruent isosceles triangle. That gives us a right pyramid. What that really means is then that the apex falls exactly over the middle of the base. So what we kind of think of as the standard pyramid, the one we see in Egypt, right? If the pyramid's not right, then it's called an oblique pyramid, and B would be an example of an oblique pyramid. Here we can see that, perhaps this triangle on the left might be thought of as isosceles. Certainly this one on the right and the one that's around back are not isosceles, because we see that this length is probably shorter than that edge length. So what that means really then is that the apex falls over some point on the base that's not the center of the base. So a quick classification scheme for pyramids. And then the last, I guess, thing to think about is cylinders and cones. A cylinder is a set of points determined by the interiors of two congruent closed curves in parallel planes, bases, and the line segments that connect corresponding points on the two congruent simple closed curves, the lateral surfaces. A right cylinder is a cylinder where every segment connecting the corresponding points on the two bases is perpendicular to the plane of the bases, and an oblique cylinder is a cylinder that's not right. So we're really mostly familiar with the right circular cylinder, but I just want to point out that cylinders can have shapes that are not circles. I mean, this could be sort of a bean shape if you like. And if there's a bean shape top and bottom that where everything's connected, then we'd still call it a cylinder. But the one for our course, the one that you're going to investigate the most is what we would call a right circular cylinder. That's where circles are the two bases in parallel planes, and then those two circles are connected by every line that connects corresponding points. So every point here to every point here has a line connecting it, and so we sort of think of all of those lines forming that lateral surface. And then of course they come in two flavors. There's the right cylinders and the oblique cylinders. So we have an example here on the left of a right circular cylinder, and the one on the right as an oblique circular cylinder. What about cones? Cones are kind of determined really similar to pyramids. It's a set of points determined by the interior of a closed curve, the base, and the line segments connecting points on the simple closed curve to a point called the apex, not in the plane of the simple closed curve. So a right circular cone would be one like this. Its altitude intersects its circular base at its center. And an oblique circular cone is a circular cone that's not a right circular cone. So for example, if we sort of pulled the center, the apex I should say, away from its point directly over the center of the circle on the bottom, if we pull that over, we get what's called an oblique circular cone. It looks something like this. The one that we'll be of course concerned with in the course is the right circular cone on the left. Again, I think that, we see lots of examples of these in our human use, and very few examples of oblique circular cones. But it's important that you understand that both of these are cones, just of a different flavor. Okay. I'm going to pause here and get ready for another video, and why don't you go ahead and skip to the next video.